Welcome back. In this video, we're going to be talking about complex numbers and their polar coordinates in the complex plane. So I need you to recall that a complex number can be written a plus bi, where I is the square root of -1 and a and b are constants, what we would think of as real numbers. Okay, plot some complex numbers on the complex plane at the left. Okay, hopefully in Algebra 2 you saw this, at least somewhere, the idea of the complex plane, because you should have run into complex roots of polynomials, right? Or at least quadratic, and seeing that they were complex conjugates. But z equals 3i, okay, well, I probably should remind you that the axes of this complex plane, which we call C with that kind of fancy C, is the real number line, which is horizontal, which you've been familiar with for a very long time, and then this vertical axis, which is the imaginary axis, which is I times the set of real numbers. So we would have something, like I here, 2i there, 3i and 4i, and -1i, -2i below that. Okay, so if we wanted to plot some complex numbers like z equals 3i, okay, well that would be z right here, 0 plus 3i. And then w equals 2 minus 2i would be, right there. Go to 2 on the real axis, go down by 2 on the imaginary axis, that'll be w. Okay. It shouldn't be relevant to our pre-calculus course, but I just would tell you that, whereas x and y are kind of the standard variables for real numbers, for some reason with complex numbers I've seen that z and w are the more common thing. Saw that, in the courses I took, on complex variables and stuff, that's pretty much the standard. So that might be something you see here and there in this class as well, because that's something we do. We use, standard mathematical notation. Okay, but what we can do is we could describe the location of each of these complex numbers or any complex number in the complex plane using polar coordinates. So the key fact here that you need to know, and this is really all I got to tell you in this video, is that a plus bi can be written as r cosine theta plus r sine of theta times I, where a is r cosine theta and b is r sine theta, just like x and y in the regular plane. So if we're asked to write the polar coordinates of w and z, I'll just start off with z because it looks a little easier. I'm thinking about r and theta. How far is it away from the origin? Well, it's 3 units away up the imaginary axis. And it looks like it's along theta equals pi over 2. So I'm going to say z can be written as r cosine theta plus r sine theta I. Okay, now we know that if we go and evaluate cosine of pi over 2 and sine of pi over 2, we're going to get 0 plus 3i. Okay, and that's kind of the point, is that these are equivalent. And they can test you on this in multiple choice, and that's why we're not going to simplify our answer, because polar is not eligible for free response testing in AP Precalculus. I need you to be ready for multiple choice situations, and I've seen a lot in AP Classroom that are, leaving it kind of unsimplified, and which of these is the right expression. And of course that is testing the highlighted information. Do you know that these two things are equivalent? Okay, and for w, I'm going to say, all right, well, r is going to be, that's going to be 2 root 2. And I would say you could either believe me on that, or you could do r squared equals x squared plus y squared. And, I think you definitely should, either see why that's true or convince yourself of it. Don't just take it on faith. But theta is looking like 7 pi over 4. So for w, I can use r cosine theta plus r sine of theta times I and write an expression that's equivalent, that is in polar coordinates. Okay. Now, I've got this multiple choice example for you. The graph in the figure below shows 4 points in the complex plane. Each complex number has polar coordinates r and theta. Which of the following completes the expression for the 4 points in the polar form 3 root 2 cosine theta plus I times 3 root 2 sine theta? We know it doesn't matter if the I goes in front or the back, right? 4 times 3 is the same as 3 times 4. So it's really just a question of what is theta for these 4 points, right? Because if it's 3 and 3, we will have 3 root 2, just like I kind of said earlier. It's like, what is theta here? Well, I would think, this one right here, that's looking like pi over 4 to me. And this one over here, the next one, that's 3 pi over 4. If I draw this right, that looks pretty good. 3 pi over 4. If we look at this, this is a 90-degree angle worth of rotation when I go from one theta to the next rotation. And a 90-degree angle, that's pi over 2. So I could say, you know, I'm expecting pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. I would think pi over 4 plus pi over 2k, where k is 0, 1, 2, and 3. But they were talking about k equals 1, 2, 3, and 4. So my early hypothesis is B. But I'm a little thrown off by the k values there. I'd expect that it would have been 0, 1, 2, and 3. So really the question is, what's up with this k equals 4? Okay, when k equals 4, theta would equal pi over 4 plus pi over 2 times 4, which is pi over 2 plus 2 pi. And it's like, oh yeah, I'd be all the way back to where I started. So I'd be right there. Okay, and so now I feel good about that answer choice. I think, you know, pi over 4k would be if we had all of these plus the ones on the axes as well. Okay, that's, you know, we could have done that as well, but then k would have needed to equal 1 through 8, and I might not have had enough room to write on this example. The ones that start with pi over 2, those aren't going to work because, you know, pi over 2 is not a solution, and nor is, I think D would be probably the next most appealing, because you're like, okay, equals 1, pi over 2 plus pi over 4 is 3 pi over 4, and then thinking it'll go to the other 3, but that one will not work. Okay, so I think that's all the examples I got for you on this. You'll see that there's not too much on this on the homework. This is not a big deal in the overall picture of AP Precalculus, but right now what I really want to emphasize is that the only two things you're expected to know about complex numbers in AP Precal is the fact that roots of polynomials with real coefficients come in complex conjugate pairs, and this business we're talking about right here, talking about polar coordinates of complex numbers. You don't need to know anything else. I've got a little separate bonus discussion for us about the nth roots of unity that I'll save for a separate video, right? Clearly labeled an extension of AP Precal. But that's really all I need to tell you about complex numbers and their polar coordinates in this video, so thanks for watching.